In this tutorial, I want to demonstrate how we can perform a one-sample z-test in Excel. So we are going to do a one-sample z-test. And z-test is based on the normal distribution. And we can use a z-test when we have a known reference standard deviation. So when we know the standard deviation of a population and we have a sample where we believe that this sample comes from this population, we can use the z-test if we have this standard deviation of the population. If we don't have this standard deviation of the population, then we would have to estimate the standard deviation, and we could no longer use the z-test and the normal distribution. We would in this case have to use a t-test, but luckily in this case we have this reference standard deviation. So how can we deal with that? Well, the first thing that we need to do is we need to, we have some measurements. Let's say these are biomarkers of some patients here, and the biomarker is given in milligram per decimeter cubed or milligram per liter. So here is a sample of patients. So here, that's our sample. And these reference values are from healthy volunteers. And what we basically want to find out is whether this sample could come from a population of healthy volunteers. So what we do in the first place is we calculate the mean of our sample. And here's the equation and the built-in formula for Excel. So we just simply calculate or put in equals mean, and then we highlight the cells C2 to C7, C6, and we get the mean. So the mean of this sample would be 68.72. And the reference mean is 67.2 milligram per cubic decimeter. We now also need to calculate a standard error of the mean. So that is usually abbreviated by SEM. That's the standard error of the mean. And for the standard error of the mean, we can use the equation standard deviation divided by square root of the number of observations. If we don't have this standard deviation, we would have to estimate it from the standard deviation of our sample. But in this case, we have the standard deviation. That is this value here, 2.56. And we can actually put this into our equation here. So here we can calculate the standard error of the mean. That would be the standard deviation that we've been given, 2.56, divided by square root of the number of observations, and we've got 5 patients whose biomarker concentration we measured. And we get a value of 1.145. for the standard error of the mean. We now can calculate a z-score, and the z-score is nothing else but a sort of a standardizing of the, it tells us how far away, how many standard deviations the means are apart. And the z-score is defined as the mean of the sample minus the known reference mean divided by the standard error of the mean, by SEM. That's what we just calculated here. And again, we can nicely calculate that in Excel. So we just simply take the mean that we just calculated minus the reference mean and divide it by the standard error of the mean that we also calculated, and we get a value of 1.33 for the z-score. Okay, so what does that mean in a way? Now, if we are just simply looking at a normal distribution, so let's say here is a normal distribution which is distributed around the mean, and if it is normalized, then the mean would be 0. And so that is a standardized normal distribution. Standardized normal distribution around the mean of 0 and a standard deviation of, let's put it as a standard deviation here. So that's our standard deviation. What we are basically asking with this z-score is, what is the probability of getting a z-score of 1.32? So here we might have a z-score. Here this would be 1.32. 1 would be around here. 2 would probably be around here. So we are asking, what is the probability of getting a z-score that is higher than 1.32 or equal to 1.32? And if we are using a two-tailed test, we are also asking, what is a z-score that is smaller than negative 1.32? Or I should probably say 1.33 here in this case, if we do the rounding properly. So we are trying to find from this normal distribution the probability of observing a value that is either smaller than negative 1.33 in z-score or larger than positive 1.33 in the z-score. And so we can do a little bit of hypothesis testing, and like with any kind of hypothesis testing, we start off with a null hypothesis. So here the null hypothesis would be the mean of the sample that we take, the mean of the underlying population, I should say, the mean of this underlying population that we have here, and I denote it as mu, minus the reference value, and that would be this value here, equals 0. It means that the sample from which this population is taken indicates a population, and that this population, which we don't know, but this population is identical to a population defined by the reference mean and the reference standard deviation. That is basically what this null hypothesis says. The alternative hypothesis is that the population mean from which we have sampled is different from this reference value. So these are the two null and the alternative hypothesis. We would set a significance level that gives us sort of a decision tool, And we can set it to whatever we want, but usually this significance level alpha, which is also called type 1 error, is very often set to 5%, which is the same as 0.05. And we set up a decision rule, and we say if the p-value, the probability to find these z-scores, if this p-value is smaller than our decision cutoff point alpha, then we reject the null hypothesis and we accept the alternative hypothesis. Likewise, if we find that the p-value is larger than alpha, we fail to reject the null hypothesis, or in other words, we just simply say, right, the population from which we took this sample and the population that is defined by this reference mean and the reference standard deviation are indistinguishable from each other. So how can we actually calculate the p-value? Well, we realistically need to do that in 2 steps. So we would calculate a p-value, the probability from negative infinity, so somewhere here, we calculate the p-value. We want to calculate the p-value of this part here, of this red part here. So what we do is we calculate the probability to get a score from, let me change the color, from negative infinity, that includes all of it to this point here. And that is, luckily, we have an Excel function for this, which calculates the p-value from the negative infinity to the point of the z-score. So here we get the p-value, and we can do that with the equation norm dot S. The S stands for standard deviation, norm stands for normal distribution, and the S is standardized. Dist, that is the distribution, and we put in the z-score, and this is the z-score that we have calculated here, so in cell C10. And we say we want it accumulated, so we want the entire area under the curve up to this point. And we get a value of 0.91. So 91%, or there's a 91% probability that the data would lie in this light blue part. So 0.908. Let's put it this way. And we can calculate the red part, therefore, as 1 minus 0.908. So that would be 0.092. Because we know that the area under a probability distribution, whatever this distribution is, which goes from negative infinity to positive infinity, the sum is always adds always up to 1. So the light blue is what we've calculated, and the red one is this red part here. So that is basically this right part of the curve that we've calculated. And we can easily do that, and that is 0.092, as I said previously. Now we can also calculate or do the same calculation for this part here that we have on this side, which we would use for a two-tailed test. And again, what we do is we calculate from negative infinity to the negative number of the z-score, as I've indicated here. So we can do that again with the normal S standardized distribution, and this time we put in the negative z-score that we've calculated here, and we say we want the values accumulated. And not terribly surprising, we get the same value of 0.082. So we get this same value here. And we can now combine the p-values of the left tail and the right tail and just simply sum them up and get a total p-value of 0.18. So that is our p-value, our combined p-value. Now we notice that the p-value is certainly larger than our alpha, so 0.184 is larger than 0.05, and therefore we go back to our decision rule and say the p-value is larger than alpha. We fail to reject the null hypothesis, so we can say there is no difference between the population mean, for our sample from which the sample was taken, and the reference values. So in other words, the reference value and the population are not in any way statistically significantly different. So this is how you can perform a one sample Z-test. I hope it makes sense, and thank you very much for watching.